I'm Haile Owusu. I'm the chief data scientist at Mashable, and I wanted to talk to you about what I think is a really interesting instance of the irrational exuberance in the face of a really complicated problem that, as a practicing data scientist, was actually quite useful for me. So we find this particular instance of irrational exuberance in the prediction of weather. Now, why do I consider weather forecasting the most ancient of data science practices? Well, it should be clear that predicting weather is incredibly important. Crop yield and survivability with respect to environmental conditions are key performance indicators. If you dramatically fail in your prediction of these key performance indicators, you might die. This ancient interaction with weather was so motivating that one can well imagine that the ability to predict weather would have been highly prized. But it was also extremely rare. The early art of weather forecasting was barely an art. It rested heavily on seasonal patterns that are essentially really, really obvious to most human observers. We're talking about yearly cycles. We're talking about daily patterns. Nevertheless, some notable advancements beyond seasonal seasonal included observations of complicated astronomical phenomena, certainly complicated for an ancient person. In general, though, most weather prediction up until very, very recently has been complete bullshit. In general, in many societies, lots and lots of weather prediction and sort of appeasing the weather gods has involved things like slaughtering animals and slaughtering people and so on. Sorry. And one particularly interesting way of predicting storms I found fascinating was the idea that you could stick a frog in a jar. And by the behavior of the frog in the jar, you can anticipate a coming storm. I think this is bullshit. I'm not sure. So, how did something so critical, so important, actually achieve the patina of what we would consider a quantitative science or data science? Well, actually, it turns out it's obviously fairly recent, but it at least in the reporting of predictions, rests on a particular fellow by the name of Admiral Robert FitzRoy, British Naval Admiral. He is known for a variety of things. It's kind of hard to tell which he's most famous for, but he was actually the captain of the Beagle that took Darwin to the Galapagos. But actually, I think his real primary claim to fame, as opposed to second fiddle to the great genius Darwin, was as somebody who decided that it was particularly important, despite inaccuracy, to present predictions for weather. In the 1850s, Admiral FitzRoy was particularly concerned about how storms essentially decimated ships and the men manning them. And he decided that, and it's fascinating to me that he decided to take this leap, but he decided that the time was ripe to start displaying and pronouncing predictions for storms. He actually, in 1854, presented the first meteorological report in 1861, presented the first meteorological report in the Times. It involved a series of basic meteorological readings in a variety of cities in the UK. And actually, he was also a bit of a data visualizer. This is not a computer-drawn diagram. This is actually something that he drew by hand as a way of trying to predict the large-scale behavior of coming weather patterns. When he first proposed this meteorological meteorological report to the House of Commons, they laughed at him. And they laughed at him because the prevailing belief, despite all of the mythology, is that weather was far, far too chaotic to predict. You certainly wouldn't want a government patina behind a prediction for fear that it would be taken too seriously. But he persisted, and he won a regular report in the Times. Now, the reports to the Times were met with varying degrees of satisfaction. Admiral FitzRoy's. One report was that Admiral FitzRoy's weather prophecies in the Times have been creating considerable amusement during these recent April days, as a set-off to the drenchings we've had to endure. April has been playing with him roughly to show that she at least can flout the calculations of science, whatever the other months might do. This was relatively gentle, actually, as a commentary on the quality of his predictions. There were worse. Yesterday at 2 o'clock, we received by telegram Admiral FitzRoy's signal of a southerly gale. The gallant meteorologist might have sent it by post, as a gale commenced the day before and concluded fully 12 hours before the receipt of warning. Oh, I'm sorry, I actually repeated those. Anyway, that's the nature of the quote. Now, again, this is actually really before the advent of a really hydrodynamic description of weather patterns. Essentially, what he had was regular data reporting and the telegraph, which meant frequent communication of that data to people who could make decisions. And just a crazy belief that you could, essentially a day beforehand, make a prediction that would be of benefit to sailors in particular. Tragically, the Admiral's predictions were met with decreasing levity, and eventually, actually, the regular reports were stopped, and there were complaints from the government essentially about the cost of broad-scale telegraphing of these predictions. This was deeply, deeply saddening to a man who was very passionate about his predictions, and so at some point he made his last prediction, kissed his daughter goodnight, and then killed himself. But for our
data scientists.
Exactly. I mean, if you've ever found yourself making a prediction that for which your business sort of rests very heavily, and if you've made the wrong prediction, you probably know what he felt like, even if you didn't do what he did. But his irrational exuberance in the face of one of the world's most complicated problems still bore incredible fruit. The reports led to the Met Office, and 150 years later, this is a site of meteorological study that involves well over 1,000 people, and an investment on the part of the British government of about £80 million. This is obviously something that was incredibly, incredibly important. And anyway, so Admiral FitzRoy was not not in of himself the pioneer of the quantitative art of weather forecasting. Many people have been participants in it. It is an exhaustive problem that involves. So if you look at the image on the left, there's essentially a grid pattern, wherein part of the process of weather forecasting, and really a huge chunk of the advance for weather forecasting has been the exhaustive measuring of weather conditions around the globe. notably with weather, that is insufficient to solve the predictive problem because, of course, weather is chaotic, and so it's highly sensitive to initial conditions. You can show rigorously that decreasing the size of these grid points gets you only so far in terms of prediction. There's been an enormous amount of effort to improve quantitative models beyond just the initial conditions question. And part of the reason that we have gone from a situation where you could laugh at the idea that you could predict weather a day in advance, now we have basically reasonably good weather prediction 6 days in advance. And we can actually predict emergent storms if, these days we have hurricanes, and though they are clearly not perfect, they are surprisingly accurate and vastly more accurate than they were even 10 years ago. So, why am I talking about weather? So at Mashable, we forecast the future of content. We're a publisher, and we obviously have a staff of writers who write a ton of content and generate a bunch of video. But internally, we're also interested in predicting in advance how well that content will do. And when I first joined the company, in addition to the variety of tasks that one has to undertake as a data scientist at a media company, this was the primary draw and the part of the company that I ended up spending most of my time on. But I was essentially tasked with trying to figure out how things go viral. And I was tasked with trying to figure out essentially a separation between things that have a pedestrian sharing behavior and almost storm-like quality to them. How do we do this? Well, we built a crawler to examine not just our content, but a vast array of content on the web, as much as we possibly can find, actually, in an adaptive system that essentially tells us where to find interesting content. So we crawl on the order of about 1 million pieces of content daily, and of those URLs, we have some smaller fraction that are sort of socially interesting. That is to say that they move on Facebook and Twitter, LinkedIn, Pinterest, all of the popular social networks. We collect a wide array, millions of data points on that aggregation of content, and we try to predict the future of it. So this is kind of a mad proposition. And when I first was presented with this proposition, I don't even know quite whether the CTO who proposed this as a plan of attack knew how complicated the problem is. Because essentially what we're trying to do is to figure out how an object like this evolves over time. So this is a graph, an evolving graph in time, and each of these nodes are a user. Some user that has come to the content in question. This was an article that was written by one of our writers about an airline company called WestJet. And over time, we find edges between nodes where that indicates some sharing behavior between the nodes. And you can see that, so obviously the center of this tree has quite a lot of activity, but there's a lot of complicated branching that happens off of the central node. And this was my task, trying to figure out how something like this grows over time. And then do this replicated over tens of thousands of URLs daily so that we can get an aggregation of which are the better performers. So to highlight how difficult this is, there was a really lovely paper written by the good folks at Microsoft about the complexity of this problem. And what the complexity of this problem really boils down to is that you have a wide variety of graph topologies that imply different amounts of sort of viral sharing, sort of organic passing on. And it's very difficult to distinguish a primarily broadcast phenomenon from a much more complicated multi-sharing type of, sure. Sorry. So, when the CTO mentioned this to me, I was like, I thought this was a mad project. But I I rather decided that it was a project that we could undertake. So we built out a product we call Velocity, which offers such a prediction. I won't go into too much detail, but suffice it to say that we offer a bunch of different metrics, but include the real-time metrics, predictions about how much sharing activity each piece of content will receive, and the amount of time it will take to achieve that total amount of sharing. This is what in a detailed look at our predictions is for an individual piece of content. Sometimes we are quite good at this. So this is a graph of the actual behavior of the content, and this is so in blue is the actual sharing behavior of the piece of content, and in yellow is the prediction that we make for it over time. Other times, the prediction that we make is a little bit less accurate and with quite a lot of variation, but essentially we capture the overall behavior. There are complicated changes in the trajectory that are hard to predict in the absence of that granular graph information. And then sometimes we're really, really terrible. And this is because, well, it's a difficult problem. The problem of figuring out social diffusion has a lot of overlaps with whether, again, a certain sensitivity to initial conditions. You chop off a central node in a graph, and everything downstream is something that probably won't participate in your cascade. Nevertheless, we actually do reasonably well. We are able within about 5 minutes to get about 75% accurate with our predictions for overall sharing behavior, with increasing accuracy over time. And these results actually compare favorably with the results found by folks at Facebook, for example, who actually have all of the granular information that we don't have about the actual graph structure on which these cascades happen. We are looking to expand our ability to model this complicated problem out using information from something we call knowledge graph, where we collect very, very granular information about sharing behavior on just our content. Bear in mind, of course, that this doesn't extend to other content that we find on the web, but this is a rather rich environment for us to develop a new model. And here's a different and slightly and a pretty picture of a cascade happening on a background environment, where the edges are colored according to which networks the sharing occurs. And with that, I'll leave it.
Turck, please join me.
Sure.
Thank you. This was awesome. A little bit to the as a sort of a response to the previous talk. How do you think about build versus buy for something like this? I mean, how much have you guys done in-house in terms of building the model, so even the infrastructure to enable you to do that, versus working potentially with outside vendors?
Yeah. So in everything that the entire structure of this app, Velocity, was built in-house. I mean, really, we built it from the ground up. I have the great pleasure of working with exceedingly talented people. In particular, our chief architect built this from the ground up on Rails. With respect to the model, that's definitely something that we built in-house. Really, because we obviously have an interest in and have actually licensed licensed Velocity out, we haven't used any pre-existing models for predictions. It was very important for us to have something that was obviously accurate, but also something that would be hard to mimic, to be frank.
Okay, terrific. Do we have questions here?
Yeah, hi, great talk.
Hi, thank you.
Technical question, or
Please.
semi-technical. So in one of your first illustrations, you explained that the nodes were readers and the edges were different kinds of sharing between readers that you had refined over time.
Yeah.
Could you go into that a little more? What beyond the simple sort of binomial shared relationship could you use? Is it how quickly they shared? Is it how often they shared?
Oh,
what do you mean by refined?
Sorry, yeah. When I said different kinds of sharing, I was probably being really, really imprecise. So that graph is simply a graph. Each node, again, is a viewer of the piece of content. An edge between them is simply the statement that we know unambiguously that by some means, their particular view of that content was derived downstream from the view of the out degree neighbor. So, the in degree neighbor. So that was a kind of a primitive version of our graph data collection. So, in the last couple of slides I showed the knowledge graph. There we have much more interesting information about what's going on the edges. So we can tell essentially where we have some information about where that share would have occurred. Other pieces of information, things like device type, the time that it occurred. We have quite a bit of information. It should be noted that the edges between the graphs are not necessarily the edges that you find on the social network. So the fact that two people or two users would have had a shared event between them does not imply necessarily that they are friends on the associated social network. There are secondary processes by which you might have been downstream of a particular viewing event. I don't know if that answers your question.
Good.
Hi, I'm just broadly interested. How has the ability to anticipate how content goes viral changed or is changing journalism? Because that's a very different emphasis
Yeah,
that it's placing.
Sorry, I didn't mean to cut you off.
Go ahead.
No, that's a really excellent question. So, I probably should have been a little bit clearer as to why we wanted to pursue this. So, obviously there is just the basic desire to better our competition by being able to jump on a story faster than. So, we have notable instances wherein our editorial staff has used the dashboard commensurate with velocity, and they've seen something that we've predicted to do really, really well in the future. And they've either written a comparable story or a response to that story. And we actually find that the top end of our content, those stories that are viewed very widely and shared very, very widely, the overwhelming majority of those are sourced from velocity by our editorial staff. In general, what we find is that using velocity on a regular basis as a curation tool and as a source tool tends to shift favorably shift the performance of our content. It also is very useful in doing broad aggregations of content. So writing about memes, for example, or writing about broad events. If you can see that in aggregate that's stories about a certain something seem to be rising, and you can anticipate that they'll rise to a high degree, you can basically participate in that conversation.
Okay, one last question quickly, whoever is closest.
Is there an easy way to block the advertised content?
Apologies, the gentleman behind you.
Yeah. Yes, I have a very general question. So, data science can improve your accuracy of velocity by 5%, and another scientist that can sell 5% more extra of their product to other customers. Which one's more scarce? Which one's more preferred or valuable?
That sounds like a really interesting question. I'm not sure I understood it though. So sorry, go on. First, you could explain.
So let's say you have two options: a data scientist that can improve the velocity performance by 5%,
yeah,
and another data scientist that can sell make 5% extra sales compared to the regular data science. Which one is more valuable?
So, Well, not coincidentally, one of our data scientists is in the room, so I would say that the investment would be on the data scientist who can make things 5% more accurate. So 5% under the circumstances is really quite a lot, actually. I think the previous speaker noted that certainly in Kaggle challenges, and I think quite generally in data science, that those last increments of accuracy are incredibly difficult to achieve. So I'll take the 5% accuracy. I mean, really, yeah, I'll go to the bank on that extra 5% accuracy, if that answers your question.
All right, wonderful. Thank you very much. This was a
Cheers.
terrific
Thank you
talk.
very much. Thank you.